Thank you. It's all right, Earthlings. I come in peace. Do you ever have one of those days where you have a great idea and then 10 minutes later you begin to think, maybe that's not such a great idea? Yeah, anyway. It's Blue Dot. We do anything here, right? We're a bit different, so. Right, okay. The good news is I am not going to stay looking like this for the whole talk. I'm certainly... You liars. Okay, just a summary first. Well, actually, I'll do a survey, even though I can barely see a thing. Hands up, wave your hands wildly if you believe there are aliens out there. Yeah, so, and now, if you believe some of those aliens might be perhaps as intelligent, maybe even more intelligent than us, go do-do-do-do-do. Yeah, so quite a lot of you believe in aliens, and quite a lot of you can't really sing very well, but that's all right, that's okay. So I'm going to give a bit of a mixed talk. So I work on exoplanets, as David was saying. I work on exoplanets. Planets are out of the stars. And quite a lot of the interest behind that for a lot of people is the possibility of alien life, maybe even the possibility that we might be able to go to another planet, an Earth 2, something like that, to live on in the far distant future. So I'm going to kind of skirt around those, how we detect exoplanets, how we try and characterize them, what do we know about the potential for habitability, and then more speculative, how we might be able to contact aliens on another planet if they're intelligent and we kind of understand that, and a little bit about towards the end about the physics of the possibility of traveling, interstellar travel, basically, okay? So some of this talk is something we might be able to achieve in the dim, distant future, but it's not going to stop me talking about it. Okay, it's a numbers game, right? So whether there are planets, what kind of planets they are, whether they're habitable, really depends on the number of stars. And this is a view of our night sky. And our eyes are going to get more sensitive here. We're going to start to zoom in a moment on that night sky. And as we zoom in, these are real images. They're taken with more and more powerful telescopes as we zoom in. Nothing's sort of, simulated here. And we're going to see what's between the stars that we ordinarily see in our night sky, okay? And whilst you're watching that, I'm going to do a very quick costume change. So hopefully I'm a middle-aged man in a morph suit, for goodness sake, right? So, yeah. Yeah, so anyway, I am going to change, because otherwise I'm going to be sort of a bubble of sweat by the end of this. So hopefully I'll time it. You might have to watch it twice or 3 times, or maybe you'll watch it for the rest of the show, who knows. Anyway, here we go. It's going to be like that, is it? You're really wondering now, aren't you? Look at the picture, for goodness sake. So what do we see now? What's filling that frame there? It's no longer stars, right? So we zoomed in on all the stars. All those stars are in the Milky Way, our galaxy. We've zoomed into a tiny, tiny patch of sky. And amazingly, it's not empty after we run out of stars. Best bit, Marks and Spencer slippers. Oh, middle-aged bliss once again. Thank you. So we've now got a picture that's full of galaxies, and we've zoomed in quite a way here. So the amazing thing is, this last image was taken with the Hubble Space Telescope, and it's one of the deepest images ever obtained. And there wasn't a special place that was picked. This is typical. There are other similar images that have been taken in other places in the sky, and we see exactly the same. We see in between all the several 100,000 million stars in our galaxy, in between all those is several 100,000 million galaxies covering the whole sky. Each of those, on average, containing of the order 100,000 million stars. So when you multiply all those numbers up, you've got some number followed by about 22 zeros after it, okay? So that's an awful lot of stars. And so you begin to think, yeah, well, even if it's quite difficult to form planets, there's still, I presume, a lot of planets. And it kind of makes a lot of us think that the possibility of life, that surely there is life out there. So we do detect planets, and this is one of the methods that we use to detect it. This is the transit method, and this movie here shows how that method works. Now, we've got a star, we've got a planet orbiting it, and if our line of sight is in the plane of its orbit, then we'll see it pass in front. We won't see it like this, you know, a sort of circle passing in front of a great big star. Stars are just points of light to us, apart from the sun. So we just see a plot like this. We plot the light of the star versus time. We see a dimming. We see a dip in the plot. And the smaller the planet, the smaller that dip. And if there are several planets, then we'll see a bunch of dips, or dips on top of each other. So we can work out that there are planets there. We can work out their orbit, how long they take to orbit around their host star. And we can also investigate multiple planet systems. So it's a pretty cool technique. And the Kepler satellite, NASA's Kepler satellite, has used this technique to fantastic effect to map, well, to detect several thousand planets. This is a really cool simulation. The code was written by Eamonn Kerins. I've dabbled with it to try and correct for the fact that Earth-sized planets, which are tiny, are much harder for Kepler to find than the big puffy Jupiter-sized planets. Okay, so I've corrected for those sorts of bias. And when you correct for that bias, and in green here we've got the orbits of the solar system planets. You can see Earth near the center there. You can see lots and lots of planets, similar size, similar temperature to Earth. And I've labeled some of the ones that are about the same size as Earth and at about the right distance from their host star, that if they have water on them, we would expect it to be in liquid form. So lots of potentially habitable planets out there. So Kepler's found a load of those, and we've got, NASA has launched the TESS mission, a sort of successor to Kepler, which is finding planets, is looking at a much larger area of sky, and it's going to specialize in looking for planets closer to us, basically, so we can follow them up in detail. So this was probably one of the most exciting discoveries of recent times made using the transit method. This is an artist's impression. This is the TRAPPIST-1 system. So TRAPPIST-1 is a star, quite a low mass star, just over 10% of the mass of our sun, so it emits quite a feeble light. But we found 7 Earth-sized planets orbiting that star. Okay, and they're in quite tight orbits around that star. Some of them only take literally a few days. But some of them are in this sweet spot, the so-called habitable zone, where if they have water on them, we would expect it to be in liquid form. Now, we don't know yet that they do, but that's ongoing work. So we've got, this is only 40 light years, sounds like a long way away, or 40, yeah, it's about 120 light years, so that does sound like a long way away, but actually there are very few stars in our galaxy closer than that, okay? That's less than, it's about 1% of the distance, less than 1% of the distance across our galaxy. So these are one of our nearest neighbors. Now, that's not the only method we use. I'm not going to discuss other methods because actually one of the take-home lines from my talk here today is that the transit method is quite a special method if we're interested in trying to detect aliens. All right? I'm going to propose that it is a special method and try and convince you that it might be. Okay? But just to fill you in, we use a range of other methods. Some give us the planet's size, like the transit method. Others look for the effect of a wobble on the host star due to the weight or the mass of the planet orbiting it. okay? So, and we're able to detect the motion, the wobble of the host star to incredible precision these days. In fact, if you need to detect the effect of the Earth on the sun, what kind of wobble does the Earth give the sun? It makes the sun move by about this speed. It makes it move something like that, I'd say. So about 10 centimeters per second. That's, I think I can stop doing this now. I think you got the idea. Right, so about 10 centimeters every second. Which is tiny. You know, this is a star which is 700,000 kilometers in diameter, 100 times the radius of the Earth. But we have instruments now that can measure that kind of wobble down to of order 10 centimeter per second precision. So the exciting thing is in the next few years we will expect to be able to measure Earth mass planets using that technique. Okay, so we've got techniques that can measure mass, and we've got techniques that can measure size, from which we can compute the volume. And very often, teams collaborate to do both around a given system. So whenever a system is in transit, the teams who are measuring mass, the radial velocity teams, very often observe those same stars in the hope of seeing the wobble too. Because if we get the size and we get the mass, then we get the density, the average density of a planet. And that's pretty cool, because if we know the average density, we can begin distinguishing between whether a planet is a big ball of gas like Jupiter, with a density of maybe about 1 gram per cubic centimeter or less, or whether it's a planet more like Earth, a rocky planet with a density of maybe 4 or 5 grams per centimeter cubed. So this is a really important thing to be able to do, and once again, the transit method is an integral part of doing this. So here we're going from planet detection to planet characterization. Okay, and there's more and more effort in the field I work in to do that planet characterization, which is kind of amazing. I mean, the exoplanet field is really, really young. Okay, the first detection was 25 years ago. In fact, it came after I did my PhD, so it's quite depressing for me. I teach this subject, which is more recent than my PhD, and I teach it to students who are also born after my PhD. So if anything makes you feel old, that's it, I can tell you. But can we do more than that? And the answer is yes, actually. This graphic here, what it's showing you, it's showing a transit, okay? But what it's showing is that if you observe a planet with an atmosphere around it, depending on which color you observe in, will depend on how deep that transit looks. And the reason being, right, what's one of the most common questions in science that you get asked by your child? It's something like, why is the sky blue, right? And the reason the sky is blue is because our sky is actually very opaque to the blue light from the sun. And it's reasonably transparent to green light, and it's even more transparent to red light. And that's a scattering process known as Rayleigh scattering. It affects blue light very strongly. It doesn't really affect red light. So if we're observing, or if an alien was observing the Earth transiting the sun, they would think that they would observe that the Earth looked a little bit larger in blue light, because the sun's blue light wouldn't be able to get through the atmosphere. And it would look a little bit smaller, the transit, in red light, because the red light would go straight through the atmosphere. It'd look pretty invisible, okay? So we'd only get the ground blocking out the sun's light. So if we observe at different wavelengths, different colors of light, we'll observe different depths. And if we do that, then A, we know there's an atmosphere there, and B, we can say something about the characteristics of that atmosphere. So here's our blue sky on Earth, exhibiting Rayleigh scattering. And in fact, a student of mine, together with myself, we formed a survey called SPEARNET, where we are probing planet atmospheres for a wide range of planets using a global network of telescopes. And we've observed Rayleigh scattering on a Neptune-like planet, GJ3470b, fantastic name, I'm sure you agree. And you can see basically this plot going from right to left. We're going from red light to blue light, and on the vertical axis there is basically the size of the planet. And you can see the planet is looking bigger and bigger and bigger in bluer light. And that's telling us there's an atmosphere there, and it's behaving a little bit like our own atmosphere in the sense that it's producing Rayleigh scattering effects. So if that planet has a solid surface and we were on it and we looked up at the sky would be blue, which is pretty nice to know, considering we can't even see the planet. We only see the effect it has on its host star. And we can do even better than that, in fact, because this shows the sort of light, how light is blocked by our own atmosphere as a function of the wavelength range. So X-rays, gamma rays, ultraviolet rays, thank goodness they're totally blocked, 100% opaque our atmosphere is to those. Then we get to our optical range, and it's pretty much transparent. Over in the radio here, the reason we can build a great big Lovell telescope here in Britain, which doesn't sound like the best place to do astronomy, is because the radio sky, come clouds or whatever, is always completely transparent. It's as good as pretty much as doing it from space, okay? But look here, there's a lot of structure going on here at the edge of the optical and into the infrared. And that is a complex playoff between different chemicals in our atmosphere. Chemicals like ammonia, like methane, like oxygen, ozone, and water. And they each have their own special signature on the way in which they absorb light. So if we map this range, the optical and infrared range, at a range of different filters, a range of different wavelengths, we will hope to see some of this structure, and in turn that gives us a fingerprint of the chemical composition of that planet's atmosphere. And this kind of work has been done already on large planets, Jupiter-sized planets, okay, around other stars. And we do see things like evidence of water vapor, evidence of ammonia, methane, etc. But we don't expect there to be life on those planets. The conditions on those planets are pretty inhospitable. Over the coming years, of course, we would hope that our technology will get better, we'll get more sensitive, and we'll be able to do it on more Earth-like planets. Well, we might hope, as well as just detecting chemicals, be able to detect biomarker signatures, so evidence for life. We know in our Earth's atmosphere there's a disproportionately high abundance of both oxygen and methane combined in our atmosphere. Were our atmosphere not to contain life, it would be way out of equilibrium abundance that you would expect. The abundance is as high as it is because methane is being constantly replenished by life on Earth, by cows trumping and things like that. So that's basically evidence for life. Okay, so combinations of oxygen and methane, that's a biosignature. And if we saw high abundances in other planets, we might start to get excited. It would need a lot of confirmation to rule out other sorts of signatures, but it would be a smoking gun signature, if you like, for the existence of some kind of life on that planet. Now, we're a couple of years from doing that, maybe a decade from doing that, but we are pretty close to being able to do that kind of search on other planets. Maybe a little bit further ahead, we can look for technosignatures. So this is evidence in the atmosphere of advanced civilization. So sadly, that's our technosignature. Pollution, we're pretty much novices when it comes to advanced technology, and we're sort of dumping all sorts into our atmosphere. But in principle, that's a signature which another advanced civilization could pick up on and go, look here, we've got a bunch of noddies who just about worked out, how to fire up a coal-fired power station. So, they haven't yet learned how to clear up their atmosphere. But that would be to them, evidence of an advanced civilization of sorts. Okay. So again, we might hope to look for those kinds of signatures in other planets in the relatively near future, looking for intelligent life, basically. Okay. Well, that's how we might look for them. Let's jump ahead a little bit and think, how might we contact them or see evidence of them trying to contact us? It sounds an impossible problem. What frequencies do you look at? How do you understand messages from them? Where do you look? Etc. The parameter space is vast, and it really is vast. But there might be some hope to tip the odds a little bit more in our favor using game theory. And I'm going to illustrate this by attempting to do that here, okay? So here's my son Ollie. Give Ollie a round of applause. Ollie, are you ready to go hunting for life out there in the audience?
Yes.
Okay, great. So I've got a game, and the game involves guessing what sum of money I have written on the next slide. It's written in pounds, and it's a cooperative game. I win if you win, but it's a special kind of cooperative game in that neither of us can communicate with each other in advance. I'm not going to give you any clues, okay? And, you know, we're going to pick somebody that I don't know, etc., etc., okay? It may work, it may not work, but I think you'll understand the principle that I'm getting at, even if it doesn't work, okay? So, notionally, let's pretend I will offer you the sum of money that is written, but actually that's a big lie. What I can offer you is this very fetching mask, okay, as a memento of the idiot who stood on the stage in a morph suit. So that can go if I get a winning answer. So hands in the air. I'm going to offer this to adults simply because there's a bit of a game of psychology going on here. So you can play the game for your child if you like, or you can even pretend you're playing it for your child and keep the mask to yourself, but it's up to you. But hands in the air if you'd like to play this game. Okay, Ollie, go hunting and pick somebody.
£150.
£150, right. So it's not £150, right? So this is a sum of money you and I would like to win. We wouldn't mind getting our hands on that. £150 would be nice, though, I must admit. I'm not going to lie. So, Ollie, let's do this maybe one or two more times. Maybe someone in the middle here.
Is it £1 million?
£1 million. £1 million. God, that would be good. I think the audience would go wild if it's £1 million. It's £1 million! Keep your hand in the air so Ollie can get you this fetching alien mask here. Ollie, you're going to have to go back down. So, fantastic, £1 million. Now, if you think about it, in principle, that sounded like impossible. I didn't even specify a range of numbers there. I could have written anything. But we know it's not impossible. We know actually the odds were reasonable. Weren't nailed on, but they were reasonable. Okay, £1 million, we're used to that being a big time prize money. And statistically, when behavioral psychologists have tested this kind of idea, this sort of game theory, this number actually comes out tops on that particular question. And this is known in game theory. These kind of answers in games involving two non-communicating but cooperating participants, these are known as focal points or Schelling points, okay? So it's not a uniform choice. There are strongly favored outcomes, okay? So, and this is basically what we could try to use to look for evidence of aliens. If aliens are sending signals to us, it might be reasonable to believe that they already have an idea that there's something there to send a signal to. How might they do that? Well, the transit method, we know, is one of the most basic exoplanet techniques to find out quite a lot about a planet. We can find out that it's there, we can find out its size, we can find out whether it's habitable, we can find out whether it has a solid surface, we can find out whether it has an atmosphere, biomarkers, technosignatures, etc., okay? And we've only recently entered the game, so we are among the most simple of participants in this game. So an alien civilization, even if they have access to techniques way beyond our imagination, they might choose this technique to give themselves the widest net to cast, okay, the best chance of getting a signal back. Likewise, we can do the same. We can look for evidence of planets that might be transiting that can see us in transit. So we have an idea of planets that are potentially habitable, etc., 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 but which have that view of us as well. And we could decide to send signals to them if we chose, but certainly to concentrate hard on listening to signals from them. So that would give us a short list of planets where the odds are tipped much more in our favor. No guarantee, of course, but more in our favor, and we could spend a lot more time covering the parameter space on those. And as regards where to look, it sort of boils down, I think, to this situation. So this is our galaxy, or an artist's impression of our galaxy. And here's the sun with the Earth in orbit around it. The orbit of our planet is vastly exaggerated here, just so you can see it. It'll obviously be buried in among the stars there. But what I'm illustrating here is the orientation of the Earth's orbit. So the Earth's orbit is tilted at about 60 degrees to the plane of our Milky Way, where the vast majority of stars are. That means there are points where it dips down below the Milky Way as we're viewing it and dips down back above. And basically those lines, the two yellow beams there where the two planes intersect, that's where we will see a large number of stars who, in principle, can see us in transit, okay? So I would say those are pretty good places to start deep surveys for transiting planets with a view to looking at those in fine detail for extraterrestrial searches if we're motivated to do that. Okay, so that's fine. We can listen out, etc. But it's kind of puzzling that, well, Enrico Fermi, a famous Nobel laureate in physics, asked a question, sounded flippant in the 1950s, and he said, "Where are they?" And you think, well, that's a bit much, Enrico, expect them to turn up. But actually, it's a great question, because when you think about it, we are not so far away ourselves from being able to, we do travel out into space already, and in terms of technology, it's not such a big leap, and I'll show some examples of why I think that. It's not such a big leap that we might go out to other star systems in the relatively near future, 100 years, 1,000 years maybe, but the galaxy's been around for billions of years, okay? So that's short order. And he's saying, basically, if we're one of many intelligent civilizations in our galaxy, it's kind of surprising that some of the others who might be way ahead of us haven't been able to, for instance, build a space probe which can go out to the nearest star system, mine a few copies of itself, send those out to the next nearest stars, they mine a few copies of themselves, and so on. And when you do the numbers game, let's say each one builds 10 replicas of itself, then after 11, 12 generations of that happening, and even if they travel at the speeds we use for our space probes, a few tens of thousands of miles per hour, we can get to the nearest star in, 50,000 years, something like that. 11 generations of 50,000 years is about 1 million years. We're long dead, but it's young. It's a blink of an eye to the galaxy, okay? So in 1 million years, if we had that technology, we could colonize, we could send a probe to every single star in the galaxy. And then you think, wow, okay, it is kind of surprising that that hasn't happened to us. There's no evidence whatsoever. Everywhere we look, the evidence we see, such as here on the moon, is of us, but not of anything else, okay? So the only time we found aliens, it's turned out we're the aliens. And it is kind of weird. We're quite close to the threshold of the question that Fermi asked of other beings. Where are they? Okay. So I don't have an answer. Maybe they're just not there. Maybe they're all nice and leave us alone. But it only takes one that's a bit like us. I mean, if we get that technology, we're going to do it, right? There's no question about it. It's basically, it's Google Earth, but on the galaxy scale, right? So somebody somewhere is going to do it. So I don't have an answer, but whether we will travel to other stars is really a question of whether we master light speed, okay? Because let's face it, nobody wants to consign thousands of generations to a tin can going into deep space for 50,000 years, okay? That's not really a starter. So we need to develop light speed technologies, really, if we're going to visit other star systems. And we know the barrier there. We know the barrier. Einstein told us what the barrier is. Nothing can travel faster than the speed of light. And there is the speed of light, okay? Pretty much 300,000 meters per second. But Einstein said something else. That was one of the things he said. But he also said that space and time essentially are personal things. Okay, and why did he say that? He was trying to unify the laws of physics between observers that were moving with respect to each other, okay? The maths from Newtonian theory gets very complicated for observers moving in different ways. And he wanted to get a unified theory together so that different observers would agree basically on what the laws of physics are. And the way he did it is he said, see that number? That number is fixed. We're not going to be able to change that number. That's the speed of light. But what we will do is change how long a meter is and how long a second is. Okay, that sounds nuts, right? So if I were to shine a torch beam to Ollie, I was kind of up to measuring it, I would see the photons leaving my torch at the speed of light, at that number there, going to Ollie. Now I could be running along and fire that torch. You would think that Ollie, therefore, should receive those photons at the speed of light plus that little bit of running speed, right? But he doesn't. Einstein says, no, he will see it arriving at him at the speed of light. So what's going on? Is light kind of intelligent and speeding up and slowing down as it needs to in order to keep that number intact? Is Einstein rubbish at maths? Well, you probably believe the first one rather than the second, but neither is true, okay? It's all to do with the fact that what I measure as the distance covered by light going from me to Ollie will depend on my motion relative to Ollie. And in particular, if I approach the speed of light, then at the point I pass my laptop, I could measure a distance between me and Ollie here, which is maybe only a meter or two, enabling my light to reach him with a speed equivalent to that. He will observe my clock ticking at a different rate to him. Okay, and so he will explain it as the fact that the only reason that I thought it took shorter is because my clock was ticking at a different rate, a slower rate, okay? So that's what he will say. And so it's tempting to think, well, who's right, who's wrong? Somebody's got a correct clock and somebody's got a correct ruler. We both have. Speed, or rather distance and time become personal. That's the consequence of fixing the number, is that you give way to the fundamental units. They become elastic, essentially. And it's not a case of rulers become wobbly or clocks start going wrong or anything like that. Biological clocks will slow down, okay, as viewed by one on the other, okay? Distances between stars shrink as you approach the speed of light in the direction in which you're moving. So if I wanted to travel to Proxima b, the planet is 4 light years away, but I didn't fancy waiting 4 years, I just travel quite close to the speed of light, and I can turn it into a 2 light year journey, or a 50-meter journey if I could still be alive after the acceleration or something. So in practical terms, I couldn't shrink it to a 50-meter journey, but the principle is I could shrink the distance to something that I'm comfortable with crossing. And I think the calculations have shown that if you accelerate constantly at 1g, and then after half the journey, decelerate at 1g, and then wherever you reach, you turn around again and accelerate 1g and decelerate 1g. You get all the way out to the Andromeda Galaxy that way, within a human lifetime, within the human lifetime of the person on board the spacecraft. Okay? Andromeda Galaxy is 2 million light years away as measured by us, but it's traversable to a distance which is within tens of light years if you accelerate at 1g and decelerate at 1g constantly. The rub is your clock will be going very, very slow compared to the people you leave behind, and by the time you come back, hundreds of thousands of years have elapsed, okay, and everybody you ever knew is dead. But apart from that, you've had a nice holiday. So meters and seconds, they're the things which give, the number stays the same. Okay, well, are we ever going to do that, right? It sounds pretty far-fetched. The guy on the left here is Yuri Milner. He trained as a physicist, and these days he's a billionaire. So he's done something right, which I clearly haven't done. But he's there with the late Professor Stephen Hawking, and in the background is Freeman Dyson, a noted astrophysicist as well. Yuri Milner has made a bet. He's made a $100 million bet. He's made a $100 million bet that he can get a team together who can build a spacecraft that can travel 20% of the speed of light to the nearest star system with a planet, which is Proxima Centauri. The planet is Proxima Centauri b. It's an Earth-sized planet, potentially in the habitable zone, and who knows, it may have an atmosphere. We know its mass reasonably well. We don't know too much else about it at the moment. But he's interested in sending a probe to that planet, traveling at 20% the speed of light. It's 4 light years away, so it'll take of order a generation to get there. And he thinks that can be done maybe about 30 odd years from now, so that potentially within the lifetime of people in this audience, the younger members in this audience, he thinks they may be able to see flyby pictures of the nearest star system, okay? So how are they going to do that? Well, the spaceship is what he's holding in his hand. He's going to send something that's not much bigger than a postage stamp, and it is a fully fledged spaceship. There's solar cells on it. There's magnetometers and gyroscopes to orientate itself, communications. They'll want to stick a camera on it as well. And it's of order a gram in weight or something. And what they're going to do is attach it to a sun sail, something like the artist's impression on the right there, and they're going to fire hundreds of high-powered lasers at it to accelerate it up. And through that process, they can accelerate it up to about 20% the speed of light and send it on its way. And they can do that because it doesn't weigh very much, okay? So this will be the first time, if it happens, the first time we will have become interstellar in terms of our reach. And this really will, in my view, put the Fermi paradox, the paradox, where are they paradox that Enrico Fermi asked, really under the microscope, because we will then, the next step, the only step we won't then be able to do is to build copies of that, to get that probe then to arrive at the star system, find an asteroid, start mining copies of itself and farming those out to the next nearest stars. But how long is that last step going to take? We've now got self-driving space probes because NASA's managed to be able to shrink an atomic clock so they don't need commands back from Earth. So we'll have self-driving space probes, deep space probes. We'll have technology to reach the next nearest stars. That last step of mining something, well, maybe we won't achieve it for 100 years, 1,000 years, maybe 10,000. Really, is it going to take us 10,000 years? I can't believe that. It won't take us surely that long. 1,000 years sounds stretching it to me. And at that stage, we'll be in a position to colonize the entire galaxy. So, where are they? It's a great question, and I don't know the answer. The answer could be that they're here on Earth, we are it. That could be one answer, okay? And if that's it, then I guess we've got to look after our home in the hope that we can spread out in the far distant future. But either way, I think we are at a tremendously exciting time in mankind's understanding of the universe and in mankind's ability to go out and reach for the stars. And so I will stop there. Thank you for listening and enjoy the day.